Welcome back to the Deep Dive. Today, we're going to be diving into the fascinating world of machine learning.
Oh, yeah.
Specifically, the idea of a master algorithm.
Okay.
You know, that one algorithm to rule them all,
Right.
capable of learning to solve any problem.
Yeah, that's a tantalizing goal, isn't it? We have so many powerful algorithms today, each with its own strengths, but a single one to solve any problem. That's like searching for a universal key to unlock all knowledge.
It really does sound a bit like science fiction.
It does.
But here's where it gets really interesting.
Okay.
What if we could combine the best aspects of different machine learning approaches to create something even more powerful, like assembling a super algorithm from the best parts of each?
Yeah, that's the core of this deep dive, because on the surface, it sounds impossible.
Right.
Take the problem of generalization, for example.
Okay.
Machine learning isn't simply about memorizing data.
Right.
It's about finding patterns and applying them to new, unseen cases.
So it's not enough to just show a computer a million pictures of cats and expect it to just understand what a cat truly is.
Exactly. Even a database with trillions of records has likely only seen a tiny fraction of all possible data combinations.
Oh, wow.
Think about it. How many ways can you combine even a handful of facts?
Yeah.
The possibilities are astronomical.
Yeah, they are.
So how do we bridge this gap
Right.
between the data we have and this vast unknown?
That's a great question.
Well, that's where assumptions come in.
Okay.
In machine learning,
Yeah.
we make educated guesses about the form of the truth that we're trying to learn. It's like a scientist starting with a hypothesis.
But doesn't that risk oversimplifying things? Like assuming all cats are fluffy just because the ones in our data set are?
It's a balancing act.
Okay.
Think of it like trying to predict your friend's favorite movie.
Okay.
You might start by assuming it's based solely on genre, but if that fails, you'd expand your assumptions.
Right.
Considering actors, directors, maybe even the time of day.
Yeah.
They prefer watching.
Okay.
So finding the right assumptions is key to getting the algorithm to learn effectively.
So it's all about asking the right questions.
Precisely. And this is where the idea of different tribes or schools of thought in machine learning becomes crucial.
Okay.
Each tribe makes different assumptions about how learning works, leading to unique approaches.
Okay, I remember this. We have the symbolists, connectionists, evolutionaries, Bayesians, and analogizers.
That's right.
5 tribes, each with their own beliefs about how to best unlock the secrets of learning. It's kind of like a machine learning United Nations.
I like that analogy.
So which tribe is holding the winning ticket to the master algorithm?
That's the fascinating part. It's not about picking a winner.
Okay.
The quest for a master algorithm is about combining the strengths of all of them.
Okay.
Each tribe brings its own unique tools to the table.
Okay, I'm intrigued. Let's break this down a bit.
Absolutely.
Can you give me an example of how these tribes tackle problems differently?
Absolutely. Imagine you're trying to understand customer behavior online.
Okay.
The symbolists might look for logical rules.
Okay.
Like if a customer adds an item to their cart, then they are more likely to make a purchase.
Okay.
They excel at finding clear, interpretable rules.
So they're like the rule makers of the machine learning world.
Exactly.
Yeah.
Always searching for those.
Yeah.
Clear-cut, cause and effect relationships.
Gotcha.
Now, the connectionists, on the other hand,
Yeah.
they're all about mimicking the brain.
Okay.
They use neural networks to learn from massive amounts of data, which makes them great for things like image recognition or natural language processing.
So they're the ones crunching through mountains of data, trying to find those subtle patterns that humans might miss.
Precisely. Then we have the evolutionaries.
Okay.
These algorithms are inspired by, you guessed it, evolution.
Right.
They start with a population of candidate solutions.
Okay.
And the fittest ones are selected and reproduced to create the next generation.
Survival of the fittest algorithm.
That's right.
I like it. So they're essentially breeding better and better solutions over time.
Exactly. And this approach can be incredibly powerful for finding innovative solutions that humans might never have thought of.
Right.
Now, shifting gears to the Bayesians.
Okay.
These guys are all about probability and uncertainty.
Okay.
They use Bayes' theorem to calculate the probability of different hypotheses being true constantly updating their beliefs based on new evidence.
So they're constantly learning and refining their understanding of the world based on new information.
Exactly. They're like detectives constantly gathering clues and updating their suspects list.
I like that analogy.
And finally, we have the analogizers.
Okay.
They learn by finding similarities between things.
Right.
It's like recommending a book to a friend based on what they've enjoyed in the past.
Right. If you like this, you'll probably like that.
Exactly. It's about finding patterns and making predictions based on past experiences.
Gotcha. So each of these tribes has a unique way of approaching learning.
Right.
But how do we bring them all together
Right.
to create something even more powerful?
That's the million-dollar question. One promising avenue is meta-learning.
Okay.
It's like learning to learn.
Okay.
Instead of picking one algorithm, we use another algorithm to oversee and optimize the performance of other algorithms.
So it's like having a conductor leading an orchestra.
That's a great analogy.
Choosing the right instrument at the right time to create a beautiful symphony.
The meta-learner acts as a conductor, selecting and combining the predictions of different algorithms, creating a more harmonious and robust final output.
So it's about harnessing the strength of each tribe and blending them together.
Exactly.
But how do we decide which algorithm gets to play which part in this grand orchestra?
That's where things get even more interesting. We can weight the predictions of different algorithms based on their accuracy on past data.
Okay.
Or their confidence in their current prediction.
So it's like giving certain instruments more prominence in the orchestra.
Precisely.
Depending on the piece being played.
Exactly.
Okay, I'm starting to see how meta-learning could be a key to unlocking the master algorithm.
Right.
But isn't there a risk of creating a system that's too complex?
That's a valid point.
Yeah.
It's like managing a team of experts with very different personalities and approaches.
Right.
But luckily, there are strategies for streamlining this process.
Okay.
One of them is using what are called ensemble methods.
Ensemble method?
Yes.
Tell me more.
Think of it like a committee of experts.
Okay.
Each specializing in a particular area.
Right.
You might have one expert who's great at analyzing data.
Okay.
Another who's a master of spotting patterns.
Right.
And another who's brilliant at making predictions.
So instead of relying on a single expert, we get the benefit of multiple perspectives.
Exactly. Ensemble methods provide a framework for combining these different learners in a structured and efficient way.
So it's about taking advantage of their collective wisdom.
Precisely.
This is all very exciting.
Yeah.
But before we dive deeper into ensemble methods, I think it's important to understand how assumptions play into all of this.
Right.
We talked about how each tribe makes different assumptions about learning.
Yes.
But how do we reconcile those assumptions when building a master algorithm?
Oh, excellent question.
Yeah.
That's where things get really philosophical.
Okay.
Remember, assumptions shape how we interpret data and ultimately what we learn.
Right. And as you said, the different machine learning tribes have their own sets of assumptions about how learning works.
They do.
So how does this play out in the quest for a master algorithm?
Yeah.
Do we need to find a set of universal assumptions?
That's a complex question.
Yeah.
On one hand, a truly universal learner might need a set of assumptions that are broadly applicable across different domains and tasks.
So it's something like a set of fundamental learning principles that apply whether you're learning to play chess or predicting the weather.
Principles that capture the essence of learning itself.
Right.
On the other hand, part of the power of the different machine learning approaches lies in their specialized assumptions.
So each tribe has its own unique set of tools and techniques that are particularly well suited for certain tasks.
Precisely. So the challenge lies in finding a way to balance the need for general principles with the power of specialized assumptions.
Yeah.
It's like trying to create a universal toolkit that's both comprehensive and adaptable to specific situations.
I see. It's a delicate balancing act.
It is.
But how do we go about finding this balance?
Right.
Do we need to analyze the assumptions of each tribe and try to extract some common ground?
That's one approach. By carefully examining the assumptions underlying different learning algorithms, we might be able to identify some commonalities or principles that can be generalized.
It's like looking for those underlying threads that connect these seemingly disparate approaches.
Exactly. It's a task that requires a deep understanding of both the theoretical foundations and the practical applications of different machine learning approaches.
Okay. I'm starting to grasp the complexity of this challenge.
It is complex.
But let's get a bit more concrete.
Okay.
Can you give me an example of how assumptions play out in different learning algorithms?
Let's consider a classic example. Imagine you're trying to predict whether a customer will click on an ad.
Okay.
A Bayesian approach might assume that each feature of the ad, the images, the placement, contributes independently to the probability of a click.
So it's like assuming each piece of the puzzle is independent of the others.
It can be.
Okay.
In reality, there might be complex interactions between features.
Right.
For example, certain words might be more effective when paired with specific images.
That makes sense.
Yes.
So how would a different tribe approach this problem?
Right.
What assumptions would they make?
A symbolist approach might look for logical rules that connect features to clicks.
Okay.
For example, they might discover a rule that says, if the ad contains the word discount and is shown to users who have previously purchased similar products, then the probability of a click is high.
Ah, I see. So the symbolists are searching for clear-cut rules, while the Bayesians are working with probabilities and potential interactions.
Exactly. And each approach has its strengths and weaknesses.
Right.
The Bayesian approach is good at handling uncertainty and noisy data.
Okay.
While the symbolist approach is better at providing clear explanations for its predictions.
So it's a trade-off between robustness and interpretability.
It is.
Fascinating. And what about the other tribes? How do their assumptions influence their approach to this ad-clicking problem?
An evolutionary approach might start with a population of random ad designs and use a process of selection and reproduction to evolve ads that are more likely to get clicks.
Survival of the fittest ad. That's pretty clever.
Exactly. And this approach can be particularly effective when there are complex interactions between features that are difficult to model explicitly. Now, the connectionists would likely use a neural network to learn a complex function that maps features to click probabilities.
Okay.
The network's assumptions would be encoded in its structure
and
the way its neurons connect and activate.
So it's like saying the network has its own implicit assumptions baked into its design.
Precisely. And those assumptions might be difficult to articulate explicitly, but they would nonetheless shape how the network learns.
Okay. And lastly, the analogizers.
An analogizer might try to predict whether a customer will click on an ad by finding similar customers who have clicked on similar ads in the past.
So it's like saying, if people like you liked ads like this, then you'll probably like this ad too.
Exactly. And the analogizer's assumptions would be encoded in its similarity measure, how it determines which customers and ads are similar.
Right. I'm really starting to see how assumptions are at the heart of machine learning.
They are.
And how the different tribes each bring their own unique perspective to the table.
Yes.
But this raises a crucial question.
Right.
If we're aiming for a master algorithm that combines the strengths of all these approaches, how do we reconcile their different assumptions? Is it even possible?
That's the big question, isn't it? One possibility is that there's a set of underlying assumptions that are shared by all the tribes, even if they don't explicitly acknowledge them.
Like a hidden code.
Exactly.
That connects all these different approaches.
And if we can crack that code, we might be able to develop a master algorithm that builds on those shared assumptions. But even if there aren't any universally shared assumptions, we might need to develop a framework that allows different algorithms to coexist and cooperate, each contributing its strengths while respecting the limitations of its assumptions.
So it's like creating a society of learning algorithms.
Yes.
Where each tribe has its own culture and customs, but can still work together for the common good.
That's a great analogy. And it's a vision that captures the essence of the master algorithm, a harmonious integration of diverse approaches to learning.
Wow, that's a powerful vision. But it also sounds incredibly challenging.
It is.
Where do we even begin to build such a framework?
Well, one promising direction is to explore the connections between different learning approaches.
Okay.
As we've seen, there are often surprising links between seemingly disparate methods.
Like how the perceptron, the classic connectionist algorithm, can be viewed as a special case of a Bayesian network.
Exactly.
That was a real aha moment for me.
And by understanding these connections, we might be able to develop a more unified view of learning that transcends the boundaries of individual tribes.
I'm starting to see a glimmer of hope here.
Good.
But even if we manage to reconcile the different assumptions and build this framework for cooperation, won't we still be left with the problem of complexity?
That's another crucial challenge, and one that researchers are actively tackling. One key strategy is to develop more efficient learning algorithms that can handle massive data sets and complex models.
So it's like streamlining the learning process so it can handle the demands of a master algorithm.
Precisely. And there are many exciting advances in this area, including the development of new optimization techniques and parallel computing architectures.
This is all incredibly inspiring.
It is exciting.
It feels like we're on the cusp of a new era of machine learning.
Yeah.
One where we can harness the power of multiple approaches to unlock the true potential of artificial intelligence.
I agree.
Well, I, for one, am eager to continue exploring this path.
As am I.
But I think we've covered a lot of ground today.
We have.
So let's pause our deep dive here and pick up the conversation in our next episode.
Sounds good to me. Until next time. You know, as we delve deeper into this quest for a master algorithm, it's fascinating to consider how our very assumptions about learning have evolved over time.
You mean how we've gone from trying to program intelligence directly to letting machines learn from data?
Exactly. In the early days of AI, there was this strong belief that we could simply program intelligence into machines.
You mean like writing down all the rules and knowledge a machine would need? Almost like crafting an incredibly detailed instruction manual for intelligence.
Precisely. That's the essence of what's called good old-fashioned AI, or Joe FAI. The idea was to create a system of logical rules and symbolic representations that would capture the essence of human thought.
But that approach seems to have hit a wall, right? What happened?
Well, it turned out to be much harder than anticipated. The world is just too messy and complex. Trying to capture all of that nuance in a set of rules proved to be an impossible task. It's like trying to fit the ocean into a teacup.
Ah, I see. So the world just wouldn't fit neatly into our rule books.
Exactly. And that's when machine learning started to gain traction. Instead of trying to program intelligence directly, we shifted our focus to creating algorithms that could learn from data.
So instead of writing the instruction manual ourselves, we're now trying to create a machine that can write its own instruction manual based on experience.
Precisely. And that's the beauty of machine learning. It allows us to tap into the power of data to discover patterns and make predictions that would be impossible to program explicitly.
Okay, that makes sense. But even with this shift to machine learning, we still need to make assumptions right. We can't just throw data at an algorithm and expect it to magically become intelligent.
You're absolutely right. Assumptions are still crucial, but the nature of those assumptions has changed. Instead of making assumptions about the world itself, we now make assumptions about the learning process.
Can you give me an example?
Sure. Let's take the concept of smoothness. Many machine learning algorithms assume that the function they're trying to learn is smooth, meaning that small changes in the input should result in small changes in the output.
So it's like saying the function doesn't jump around wildly. It has a certain degree of predictability.
Exactly. And this assumption of smoothness allows algorithms to generalize from the data they've seen to make predictions about new, unseen data.
So if we know how a function behaves in one area, we can make educated guesses about how it behaves in nearby areas, like connecting the dots.
That's a good way to think about it. And this assumption of smoothness is fundamental to many powerful machine learning algorithms, like those used in facial recognition or spam filters.
Interesting. So even though we've shifted from explicitly programming intelligence to letting algorithms learn from data, we still need to make assumptions to guide the learning process.
Precisely. And finding the right assumptions is a delicate balancing act. If our assumptions are too strong, our algorithms might miss important patterns in the data. But if they're too weak, our algorithms might overfit and fail to generalize.
So it's like Goldilocks and the Three Bears machine learning. We need assumptions that are just right.
A very fitting analogy. And the quest for a master algorithm can be seen as a search for a set of assumptions that are both powerful and general enough to enable learning across a wide range of domains and tasks.
Okay, so it's not just about finding the right algorithms. It's also about finding the right assumptions. And that's where things start to get really interesting, don't they?
Absolutely. The role of assumptions in learning is deeply connected to fundamental questions about the nature of knowledge induction and intelligence.
I'm starting to see how this deep dive into the master algorithm is really a deep dive into the nature of thought itself. It's quite a journey.
It certainly is, and the journey is far from over. As we continue to develop more powerful and sophisticated learning algorithms, we'll need to grapple with even deeper questions about the role of assumptions bias and ethics in artificial intelligence.
Okay, you've officially given me a lot to think about. But let's bring things back down to earth for a moment. We've talked a lot about meta-learning and assumptions, but we haven't yet explored how these concepts play out in specific machine learning tasks. Can you give us some concrete examples?
Absolutely. Let's take the example of image recognition, a task that has seen remarkable progress in recent years thanks to the advent of deep learning.
Right. Deep learning. the rock star of the machine learning world. But even deep learning algorithms need to make assumptions right.
They do. One common assumption is that images can be represented as a hierarchy of features, with lower-level features like edges and corners combining to form higher-level features like shapes and objects.
So it's like saying the algorithm builds up its understanding of an image from the ground up, starting with simple elements and gradually piecing them together into a more complex representation.
Precisely. And this hierarchical representation is often encoded in the structure of a deep neural network, with each layer of the network responsible for learning a different level of features.
Okay, that's starting to make sense.
Okay.
But how do assumptions and meta-learning come into play here?
Well, one way to think about it is that the choice of network architecture, the number of layers, the types of neurons, the connections between them, encodes a set of assumptions about the nature of images and how they should be represented.
So it's like saying different network architectures embody different beliefs about how images work.
Exactly. And meta-learning can be used to automatically search for the best network architecture for a given task.
So instead of a human expert having to painstakingly design the perfect network architecture, we can use a meta-learning algorithm to do the heavy lifting.
Exactly. And this can lead to significant improvements in performance, as well as a deeper understanding of the relationship between network architecture and learning.
Fascinating. So meta-learning can be used to optimize the assumptions baked into a deep learning algorithm. That's pretty powerful.
It is, and it's just one example of how meta-learning can be used to improve the performance and adaptability of machine learning algorithms.
Okay, so we've seen how assumptions and meta-learning play out in image recognition. What about other machine learning tasks?
Let's consider natural language processing, another area where deep learning has made significant strides.
Right, we're talking about things like machine translation chatbots and text summarization, right?
Exactly. And one common assumption in natural language processing is that words can be represented as vectors in a high-dimensional space where words with simile meanings are closer together.
Okay, so it's like creating a map of the language where words are points in space, and the closer the points are, the more similar their meanings.
That's a great way to visualize it. And this assumption of a word vector space allows algorithms to learn about relationships between words, even if they've never seen those words together before.
So like if the algorithm knows that cat and dog are close together in word vector space, and it sees a sentence like, the fluffy cat purred, it might be able to infer that the fluffy dog barked is also a plausible sentence, even though it's never seen the word barked before.
Exactly.
Yeah.
That's the power of word embeddings, as these vector representations are called. And meta-learning can be used to optimize the learning of these word embeddings, further improving the performance of natural language processing tasks.
Okay, I'm starting to see a pattern here. Meta-learning seems to be a bit like a universal tool that can be applied to optimize the performance of all sorts of machine learning algorithms.
You're right. And that's why meta-learning is such an exciting area of research. It holds the promise of making machine learning more powerful, more adaptable, and ultimately more intelligent.
Welcome back to the deep dive.
Yeah.
In the last two parts, we've been on this quest to understand the master algorithm.
Right.
An algorithm capable of learning anything.
Yeah.
We discussed the challenges of teaching a machine to truly generalize.
Right.
The importance of assumptions.
Yeah.
And the power of combining different approaches to learning.
Exactly.
Now let's get to the heart of the matter. What might this master algorithm look like? Are there any contenders out there?
Well, it's a question that sparks the imagination. We talked about those 5 tribes of machine learning, right?
Right.
Symbolists, connectionists, evolutionaries, Bayesians, and analogizers.
Right.
Each tribe has its own powerful methods that embody its core principles.
Right, like the symbolists with their logical deductions, the connectionists with their neural networks, and so on. So are we saying that one of these existing algorithms might be the key to the master algorithm?
It's a possibility, but it's unlikely that a single existing algorithm holds the key.
Okay.
Each of these approaches has limitations.
Right.
What we're looking for is something that can transcend those limitations and combine the strengths of all 5 tribes, like finding a common language they can all speak.
Okay, so it's not about picking a winner. It's about finding a way to integrate them. But that sounds incredibly complex. Where would we even begin to look for such an algorithm?
One promising approach is to search for algorithms that bridge the gap between different learning styles.
Oh.
One such candidate is something called a Markov Logic Network, or MLN for short.
Markov Logic Networks.
Yeah.
Okay, I'm going to need you to unpack that one for me. What makes them so special?
What's fascinating about MLNs is their ability to combine the power of symbolic logic, the kind of if-then reasoning we use in everyday life,
Right.
with the flexibility of probabilistic graphical models.
Hold on a second. Symbolic logic, that makes sense to me.
Yeah.
But probabilistic graphical models. Can you refresh my memory on what those are?
Imagine a network of concepts connected by links that show how likely those concepts are to influence each other. It's like a visual map of relationships and probabilities.
So like a map of how ideas connect and how strongly they relate to each other.
Exactly. And by combining these graphical models with symbolic logic, MLNs can express both deterministic rules and probabilistic relationships.
Okay. I think I'm starting to get it.
Yeah.
So an MLN could say something like, if someone smokes, then they're more likely to get lung cancer, but also account for the fact that not everyone who smokes gets lung cancer, and some people who never smoked do.
Precisely. MLNs can handle that kind of nuance while still incorporating the logical structure of cause and effect.
That's pretty impressive. So how would this play out in building a master algorithm?
Imagine an MLN that can encompass the core knowledge of each of the 5 tribes. It could contain rules representing the symbolists' logical deductions,
Right.
probabilistic links that mirror the connectionists' neural networks,
Okay.
and even processes that resemble the evolutionaries' algorithms.
So it's like creating a grand unified theory of machine learning, all within this framework of Markov logic networks.
That's a great way to put it. And because MLNs can handle both logic and probabilities, they could potentially learn from any type of data you throw at them.
Wow.
Structured databases, text, even complex sensor data.
Wow, that sounds incredibly versatile.
They are. And MLNs are already being used in many applications.
Wow.
From understanding language to analyzing social networks and even in bioinformatics.
Okay, so MLNs are definitely a strong contender for the master algorithm. Are there any other approaches out there vying for the title?
Absolutely. Another fascinating approach is based on the idea of probabilistic programming.
Probabilistic programming. I'm all ears.
Imagine a programming language where you don't just tell the computer what to do, but instead describe the uncertainties and possibilities within a problem.
Okay.
It's like a recipe that says, add a cup of flour, give or take a tablespoon, allowing for flexibility and unpredictability.
Interesting. So instead of rigid instructions, we're giving the computer a set of possibilities and letting it figure out the most likely outcome.
Exactly. And that's the essence of probabilistic programming.
Okay.
We write code that describes the probability distributions and statistical models underlying a problem.
So we're basically teaching the computer to think statistically.
Precisely. And then clever algorithms come into play to reason about those probabilities and make the most accurate predictions possible.
That's pretty mind-blowing. How does this fit into the quest for a master algorithm?
Well, some believe that probabilistic programming could provide a more unified and flexible foundation for machine learning as a whole.
Okay.
Imagine a single programming language that could express and solve a vast range of learning problems, from image recognition to natural language understanding.
So it's like a universal language for machine learning.
Exactly. And several probabilistic programming languages are being developed,
Wow.
each with its own strengths and areas of focus. It's a vibrant field with a lot of potential.
It seems like there are many paths to explore, but no single clear winner in this race for the master algorithm. So are we any closer to finding it than we were when we started this deep dive?
I'd say we're closer to understanding what a master algorithm might look like and the hurdles we need to overcome.
Right.
We need to find ways to reconcile different approaches,
Right.
develop incredibly efficient algorithms,
Right.
and think carefully about the ethical implications of such a powerful tool.
You're right. It's a multifaceted challenge that requires ingenuity and careful consideration.
It is.
This has been an incredible journey.
It has.
We've explored the frontiers of machine learning, grappled with complex ideas, and even touched on the philosophical implications of creating a truly intelligent machine. Any final thoughts for our listeners as we wrap up this episode?
The quest for a master algorithm reflects our innate desire to understand the world and ourselves. It's a journey of discovery that will likely continue for years to come, with each step forward bringing us closer to unraveling the mysteries of learning and intelligence.
Beautifully said. And remember, even if we never find that one perfect algorithm, the search itself is pushing the boundaries of what's possible and leading to innovations that are changing our world. So stay curious, keep exploring, and who knows, maybe one of you listening will be the one to discover the master algorithm.
Thanks for joining us on The Deep Dive. Don't forget to like, share, and subscribe for more deep dives into the world of knowledge.